Our next speaker is Professor George Simon, whom we met earlier. As I said, Deputy Dean of Engineering, and he's also a Professor in the Department of Materials Science and Engineering. His area of expertise is polymer engineering and nanomaterials. His research group looks at functional polymer nanocomposites, dendritic materials, polymer blends, and electrospinning of nanofibers.
So what I want to do two things today. I'm going to wear two hats, if you like. One is I'm just going to say a little bit about the facilities we have in engineering in terms of which underpin the graphene effort, and I'll mention what I mean by that. And also want to just say a few words as a kind of a researcher about why graphene would be good to put into polymers, and also why that's interesting. And it's a new area. We're just sort of starting work in that area, and it's one that's got a lot of promise. So I'm wearing two hats. The first part of my talk, what I want to do is just make the point that we have a lot of people working in a lot of different areas, but I think what's key at Monash is that as well as the materials itself, we have a lot of ability to look at different applications. For example, membranes, we have a lot of membrane people. So as well as having the materials to make membranes, we then have people who can do things with those membranes. I want to say a word about that range of skills, and then I want to say a word about the characterisation facilities, partly to show that we can support a range of research, partly also to show perhaps maybe in other areas, other work you're doing, that we can also be involved, seeing we've got you here today. And then I said I want to talk a bit about polymer nanocomposites that we've worked on in the past and their advantages and how we think this can is a very live area for graphene. So this is just kind of a list really that I want to, I'm not going to highlight the areas that have already been talked about, but I just want to show some of the other areas that we work in because some of these graphene can be applied to these and also other functional materials as well. So we work in electrically conductive materials such as conductive polymers. As I said, we work in membranes. We have people who work in graphene membranes. We've got a much wider program in graphene and nanocomposite membranes across the faculty. We've got a very strong research group in wearable electronics. Clearly graphene could be part of that, as can other conductive materials. Printable solar cells is an important area of research that we do for modular solar cells on plastic, and of course that's relevant too. Magnetic nanoparticles for drug delivery, for hypothermia is another area we work in. Injectable hydrogels as scaffolds in the body, so all sorts of tissue engineering properties and applications. Paper-based diagnostics is an area we work in. Other nanoparticles for sensing catalysis. Modelling across a range of size scales, which is a very interesting thing, because often modelling can do things that you can't easily do experimentally and yet provides knowledge that helps you plan your experiments and applications. And I'll just throw this up as a grab bag, and I partly do it for that, so you can see the sort of the range of things that we can do, and that therefore we can support all the way through product development, from various gas and liquid permeability to looking at mechanical properties of materials, surface properties of materials such as wear and friction, corrosion. Rheology, of course, is often important in processing, a range of thermal analysis, calorimetry, mechanical thermal analysis, electrical and thermal conductivity, of course, important. Magnetic properties, micro and nanofluidics, we have a lot of expertise. Spectroscopy of various sorts, and of course imaging, and as I said, modelling. So these are sort of the areas that support the graphene effort, but also the functional materials and industry engagement effort more generally. Now what I want to do is just to take a step back and talk a bit about graphene in polymers. Now some of the areas we've talked about before, including some of the membranes, we can put a little bit of polymer in there and can make that a functional membrane. Dan talked about the idea of having a hydrogel graphene membrane. You can put polymers in there. Polymers are functional. You can increase the functionality of that. I'm not going to talk about that now. I want to talk about something that perhaps is a little closer to commercialisation, and that is the use of graphene in nanocomposites. The idea where you have a majority polymer phase and you put the nanoparticles in that area. Now, so some graphene, of course, applications stand alone, supercapacitors, graphene membranes. But like many other nanomaterials, what we find, the history shows that a lot of the applications have come in this area where we put the nanoparticles into the polymers, where we just need a few percent of the nanoparticle, in this case the graphene. And once again, keen on these sort of graphs because they're sort of useful. This shows the market for nanocomposites generally. So nanocomposites here is a polymer matrix with nanoparticles, usually only a few percent. And so these can be a range of nanoparticles. This isn't for graphene. It's growing at a rate of around 18% per year. And so polymer nanocomposites have previously been early adopters of nanotechnology, and so I'm hoping that I can engender a bit of interest in this area with graphene as well. So just as nanocomposites overall now, not graphene, and you can see that it's really spread across a wide range of sectors, from automotive, aviation, building construction, medical and so forth. So the use of nanocomposites just generally is something that can span many different industries. So why is graphene so important? Well, we're only really starting work in graphene, so what I want to give you in the next minute or two is just to show you what we've done in other nanocomposite areas and show you how that relates to graphene. The area of graphene nanocomposites is really, comparatively speaking, quite a virgin ground really for people to work in and potentially commercially exploit. So I've done a lot of work. I've worked in nanocomposites maybe for 15 years or so, and what's interesting about graphene is I've worked in carbon nanotubes and worked in nanoclays, and actually if you kind of put them together conceptually in your mind, it kind of comes up with graphene. So it's a conductive layered system that can be used. So what I'm going to do mainly is just quickly tell you briefly why you might use carbon nanotubes and nanoclays, and then put that together and show why graphene could also be useful in this regard. So what are we doing with doing nanocomposites? We're blending things into plastics. What do we have to do? We have to disperse them well. We need good interfacial adhesion to get the good properties. So we really want to get them well dispersed. And then once they're in there, we want them to adhere well to the matrix around it. So why blend? This is some work we did with nanoclay now and nylon. You can see that only a couple of percent, in this case 6%, almost doubled the modulus of the material. And 3% also increased it substantially as well. And so this is an example of where nanocomposites at a high surface area can use very small amounts of material to achieve desirable results. And it's not our data on the right, but it's a classic diagram often shown where you can see that less than 5% of filler can double the modulus of something, whereas if you use glass fibres in that nylon, you need about 20%. That's much more viscous, it damages your processing equipment and so forth. Causes degradation of the polymer. Here's just an example, by the way, where we use nanoclay in epoxy resin, Degiba, the commonest epoxy resin. We found we could get substantial increase in modulus, and at the same time we could get increase in fracture toughness. That's a paradigm that's rarely found in materials engineering, because normally you make something more rigid, it becomes more brittle. But there's, because of the surface areas and other factors, you can actually introduce good properties. What's another reason why you blend with nanoparticles? This is what we did with nanoclay. What we found is that by putting in a couple of percent of nanoclay, we could decrease the permeability, such as to oxygen or other gases, by about half or more. And so that's by the tortuous path on the far right for the gas to get through. So the nano, in this case, sheet-like nanomaterials, nanoclays, are able to introduce that. Of course, conductivity is an important one. I just showed the example here of carbon nanotubes. This isn't our work. I just showed one with PVC, where you can see that very low amounts of a rod-like material, extended material, have a very low percolation threshold, where the concentration you need to make it conductive. And on the far right, I've got some discs sort of representing a graphene or like material that would similarly that high anisotropy. Whereas if you actually use spheres like carbon black or something like that, it's usually much higher concentration required. Why blend with graphene? What about there's increased flame retardancy? Haven't really seen this with graphene, but with carbon nanotubes and nanoclays, what you find is that by putting nanoparticles, distributing them, as things burn, they tend to move to the top, and they make a layer that reduces the amount of gases that can go in and out and the amount of loss of material. So this is actually from people in NIST, where they put nylon with carbon nanotubes, and you can see on the far right that it keeps a charge. So if you had maybe a coating on a cable, that you could keep that electricity running for a couple of hours. Why blend? Another reason is thermal conductivity. And increasing electronics, of course, we want to be able to transmit. And I think Michael made the point that, graphene has a high thermal conductivity, but also carbon nanotubes likewise. This is carbon nanotube data, just another idea. So what are some potential, putting that together with the nanotubes and the nanoclays, what are the advantages for nanocomposites made out with graphene? Of course, graphene is very rigid, so we can increase the modulus. It has a high surface area, a high L-on-D ratio, if you like. It's very thin, so you can get a lot of polymer contact. You can really influence the polymer properties because of the high surface area. We know it's conductive. That's obviously useful. It's thermally conductive, so not only electrically conductive, could assist in fire retardants, it's impermeable. Graphene is impermeable, therefore it could produce gas barrier or even water barrier. The literature shows that graphene has antimicrobial and antibacterial properties as well. And it's ready functionalised. We know how to functionalise graphene because carbon-based systems have been functionalised before. So really, what is the current state of graphene nanocomposites? It's really in its infancy. Most graphene and nanocomposite work that's been reported to date has mainly been done with graphene oxide or thick many-layered graphene, and there's different ways of making graphene where there's packets of 5 or 6 together. And so it's only really coming now, including with folk in this room, where we're looking at ways to mass-produce single-layer graphene, and that's going to sort of change things quite dramatically. So there's no real simple large-scale supply of single graphene coming at the moment. It's coming, and to date, a lot of the research has really been done on the benchtop, doing solution blending of polymers and so forth. I think there's, for the extrusion and other ways of doing it, there's lots more to go. Only limited melt blending studies, as I said, mainly with graphene oxide or multi-layered graphite or graphene packets, not really graphene. Thermosetting materials are a material that is very interesting candidate, of course, because we're starting with a liquid, so it's for coatings and composites, it's a ripe area. So finally, the challenges that we have and why I think it's an interesting area to look at, we want to get good dispersion, big lateral dimensions, because we want to stretch the graphene sheets out, and we want good interface between the polymers and the graphene. And so for all of that, polymer nanocomposite graphene materials are interesting. That's what I want to say. Thanks very much.